everyone. How are we doing? We are live. Good to see you here. Catherine, good to see you here. Hannah, how about we do some My Pearson? Chapter 13 is going to be a tough one. What do you think? Do people have questions? What are people wondering? You know what I might try to do? I might try to make it real quick that I can hear the sound too. Let me go to the music. No, because I think you can hear the music right now. But it doesn't play through my headphones too. The problem. That is the problem, and I don't know how to get it to do it. Because that's what I'd like. If you have questions, let me know. Stream Deck. Go look at this. Let me look at it really quick over here. If you have questions, drop them in the chat. We can get working on something here in a moment. Output to chat, go XLR. So what if I put output to the computer? It's going to chat right now. Let's go to, there's headphones. Now I hear it, but you don't hear it. Reagan, good to see you here. You hear the music now, don't you? You hear the music and I hear the music. I like it. Okay, I need to fix some volumes on here, but... There we go. Perfect. Figured it out. I was like, I can figure this out. We got the chill music now back, and I can listen to it, and I can hear it with you. I need to change all these. AirPods. Wait, how's it got AirPods on that? Headphones. Headphones. Oh my gosh, we figured it out. Like when there's a will, there's a way. What questions shall we do? Any questions? What's up, Cameron? Good to see you here. I'm going through and changing all the volumes. Setting everything to a proper, nice volume. Brian got one more thing fixed here. A little lower. What question? Any questions? Any My Pearson? What are we doing today? What's the plan? Do we have any plan? Chapter 13, part 1, part 2. Sampling distribution of the sample mean, sampling distribution of the sample proportion. Any questions? We're just relaxing while Brian does some housekeeping right now. I'm changing a bunch of settings. I'm streaming, right? I am streaming. Interview sampling distributions of the proportions conditions. Yeah, let's go find a question that does that. Go find that. Okay, I've got a lot of these changed now. Ooh, 80s rock, we need that. I can hear the music. Let's go do that. You got it. You got it. Let's go check out a question that goes over the sampling distribution of the sample proportion conditions. Okay, what is condition 1? As we get loaded up right here, what is condition 1? We could do the homework first, you know? Not due for a few more days here. Should we do the homework first? Like, just do the full homework? We get that knocked out during office hours here. We do the full homework, yes or no in the chat. We'll probably do conditions. I bet it will. Let's go over here. It's a big homework. Let's start it up. Here we go. Okay, I'm zoomed in. Oh my gosh, there we go. So the sampling distribution of the sample proportion, probably gonna be that answer. You have to know what we are doing here. You have to understand what we are doing and why. When we do the sampling distribution of the sample proportion, we're asking about what could occur. We're asking about what could occur. So if we were to go out and talk to UT students and ask them a question like, are you an in-state student? So, are you an in-state student? Why is that proportions? This is a huge thing you have to know when doing these questions. If we ask students, are you an in-state student? Why is that proportions? And anytime we do proportions, it'll always be this kind of question. So why is are you in-state students proportions? And then you have to look at your formula sheet and say, which one of these am I doing? We're always teaching to the test on here, so let's go and look at that. Why is are you an in-state student proportions? Why is are you an in-state student proportions? So here is, we'll put review 2 in the chat. Sarah, good to see you here. It's categorical. Reagan, great job right there. Reagan's right, it's categorical. So it is categorical, and Mubots put the review in the chat. They've got all these cool emojis, so it makes it harder to pin messages now. But when you do that, if you are doing the sampling distribution of the sample proportion, you need to go to your formula sheet immediately and go down here and use this right here. Notice how this is for proportions and the other one is for means. I don't like how they changed this. There we go. So proportions is the top one, means is the second one, and you have to know which one you're using. So this is for proportions, like are you in state, are you out of state? And this one is for means, like how many jelly beans are in a bag of jelly beans? Ones that are similar to the example. kind of. So here we'll take this and can we put it over on the other one? Where's the other thing? Oh, we lost it. Okay. So we'll leave this over here and we'll use it some. An investment website talks about all this stuff, yada, yada, yada. They draw from a sample of 468 investors. Oh, no worries. Suppose that the true proportion of smartphone users is 37. What would the managers expect the shape to be? Now, you can see the answers on here, but let's review why. There are how many conditions for the sampling distribution of the sample proportion? There are how many conditions for the sampling distribution of the sample proportion? There are how many conditions for the sampling distribution of the sample proportion? There are how many conditions? There are 3 conditions. Oh my God. Well, let me open the notes here in the background. I'm going to the sampling distributions of the sample proportion. Like it doesn't exist. Oh my gosh. Well, condition number 1 is random. We need to randomly select the observations. Condition number 2 is 10%. Take less than 10% of the total population. As in, UT has 30,000 students. So if we want to take less than 10% of the UT population, we'd take how many students? UT has 30,000 students. To take less than 10%, we would take how many random students? We want to take less than this. How many students would we take if we want to take less than 10%? So UT has 30,000 students. We want to take less than 10%. And the conditions on the test, less than 3,000, exactly, Cameron. The conditions on the test literally look into this. It's like, is the 10% condition passed? So the way you do the 10% condition is, we'll write each condition here for people wondering about conditions. And so condition 1 is random. So condition 1, sampling distribution of sample proportion. Write down these steps. Good morning, good to see you here, Aaron. So condition 1 is random. How would you check to see if it was randomly selected? Which on the test will make this very clear. My Pearson questions are pretty good about it, but on the test we're super duper clear. So how would you check to see if it's randomly selected? How would you check to see if it's randomly selected? There's really only one step. How would you check to see if it was randomly selected? How would you check to see if it's randomly selected? These are the conditions right here. We can use this for any of the questions. Write these down, know the conditions. How would you check to see if it's randomly selected? How would you know something's randomly selected? I mean, this one's the easy one. No real tricks on this one. How would you know something is randomly selected? Stumping Peel this morning. Would it say random? Yep. Does it say it's random? So if it says it's random, you're good. If it doesn't, it's not. So that's it, Sarah. Great job right there. Let's throw you 1,000 points. Keep those answers rolling in right here as we keep doing some more questions. And now the next one's where people usually get stuck is when it gets to these next 2 conditions, which are going to be less than 10%. I usually call it the 10% condition just because it's easier to say 10%. So you used to hear me say random 10%, but we mean less than 10%. So first step is, or step 1 for this one is, know the population size. You can guesstimate it. Like if I said about how big is the US? Don't worry if you're off, because I'm going to say we sampled 1,000 people. And there is the reverse way of doing it too. but know the population size. So about how big is the US? I think I kind of know off the top of my head. I think it's like 360. If I had to guess. How big do you think the US is? So first off, you know the population size or have a good guess of it. What do you think the size of the US is? How many individuals in the US? This is how you figure out if you took less than 10% of the population. What do you think the size of the US is? How many people in the US? Too many. Well, it can't. Well, then, well, I mean, what if we took 100 million people in our sample? What if our sample was 100 million? There's the reverse way of doing it, because you can take your sample and times it by 10, and then there would have to be 1 billion people in the US, which there's not. So I think there's about 360 million people in the US. So know the population size. Step 2 is your sample less than 10% of it. So the population size is n, and your sample is lowercase n. It can also be checked. Additional check, you can take n divided by n is less than 10%. So right here, 1 billion is not a billion. Well, there would have to be then, right, Sarah? You got it. So 320 million. I thought it was about 360 million. I thought 360 off the top of my head. Population of USA. 330 million as of 2021. So maybe 360, somewhere in that range. 300 million, not billion. That'd be crazy. 300 billion. That's a lot. So somewhere in that range. But does any questions on this step right here? 1 billion in the US. I know, right? 3 times. That'd be crazy. So here we go. Step 3 is success, failure, condition. Failure. Okay. Now the success failure condition goes the following way. Step 1. What is your proportion? We're doing this very carefully. Step 2. What is its complement? All we're finding right here, what are we finding in notation? So you need to find what in notation, like what is your, and we'll write true proportion. So what are we writing here? What is its complement? Not p hat actually though, not p hat, because the true proportion is p. Good answers, we're throwing more points in the chat. The true proportion is p, and we're finding, oh, we got to put another 0 on that. And then we're finding q. So we will use q hat in later chapters, but right now we're finding p and q, which are the true proportion and the complement of the true proportion. Step 3, what is your sample size, which is n. And then step 4, are both np and nq greater than 10. So 10 or more, we'll never do exactly 10, but think about this. It's actually, the condition is a lot easier if you understand what you're doing. Imagine this, 40% of students are in state. So 40, now let's go 60%. 60% of, great job Aaron right there. 60% of UT students are in state. So what did I just tell you? P, Q, N, what did I tell you? 60% of UT students are in state. Did I tell you P, Q, or N? Did I tell you P, Q, or N? 60% of UT students are in state. I told you P. Now what can you find once you find P? So if you know P is 0.60, then what can you find if you have Q? Or if you, then you have Q, is 0.40. Now technically, I'm gonna throw you some points. Correct is just a little bit, just in case, because when you get to the test, remember this is proportions. For 1,000 points, make a small little correction to it. I know it's 60%, but express it as a number. Boom, right there, Cameron, exactly. Just, I want to make sure when we get to the test, like, I figure you probably are doing that, but then I just want to double check and make sure we get it right. So now think about this. Don't even do the math. If I talk to 1,000 students, how many of them do you think would be in state? This is what the success failure condition finds for you. If I were to talk to 1,000 students, how many do you think would be in state? Well, how many? 60%, but how many? How many of them do you think would be in state? 600. Great job, Hannah, right there. And notice Hannah did the math down here because n times p is 1,000 times 60%. There we go, I was doing it too. And 600. And then think about this. How many would you expect to not be in state? How many would you expect to not be in state? So if you expect 600 to be in state, how many do you expect to not be in state? 400 we would expect would be out of state. And so what do you pass the condition right here? Do you have at least 10 successes, at least 10 failures? So do you have at least, and that's what a success failure is. It's like this many of the yes case, this many of the no case. You have at least 10 successes and at least 10 failures. Now the whole point of doing these conditions is if we pass these conditions, the distribution, oh, really? Sometimes this applet gets mad if you put in too large of numbers. If you pass, really, applet, you can't do that big of numbers. If you pass the conditions, the distribution will look what? If you pass the conditions, the distribution will look what? If you pass the conditions, it will look what? Normal. Normal. That's the whole point of passing all three conditions. If you don't, because imagine if we only talk to 3 or 2 students. Now be very careful. If we only talk to 2 students, now I know it's not a whole number, but if I only talk to 2 students, how many would I expect to be in state? If I only talk to 2 students, how many would I expect to be in state if I only talk to 2 students? I'm sorry, I had to change it so you could see it visually. It was 1,000 in the example before. If you pass all 3 conditions for the sampling distribution, the distribution of the sample mean or sample proportion will be normal. And so here we go right here. If we only talk to 2 students, then take a look. Does that look like a normal shape to you? And there's that 1.2 over there on the side, the expected value. This is with a binomial distribution, but the binomial will approach a normal, which you can't. But it's on this. But here's the thing. And great comment, Sarah. It would be expected in the long run over repeated sample proportions. Like if you repeated this process, on average of the repeated process of sampling 2 students with a 60% proportion, you would see on average 1.2. And it would be, would it be? It'd be, I think it's a left skew monster, man. It's so hard to see. I'm throwing a bunch of points. I think he's got a little bit of left skew. There's 1,000 points for that right there. Because if we go, bring this to 90%, yeah. See, now it's even worse. There's 1 expected success. So it builds up on the side where the percent is, and then it skews over to the other side. It's very tiny skewed. This is where you go, la, 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 and you stop listening. The success failure condition actually doesn't really apply. I can't put that. I know. I meant to put in the other one. I'm sorry, applet. You could actually slightly have problems, but have a proportion of 50%, and it works because of the way the proportion is. So technically, if we got really specific and didn't do the 10, you would need higher ones probably at larger percentages, but 10 is usually good. So you need at least 10 successes, 10 failures, which we don't have here. So technically we should go up to this and then it looks normal. There's 10 successes, 10 failures. I love that emoji too. It's good stuff. And so if we pass all 3 conditions, so if you increase the size of the sample, it becomes yes, because when sample size increases, there are more whats and whats, which is the central limit theorem too. It becomes more normal. There would be more whats and whats for this one though. And so Reagan, good connection right there. If you increase the sample size right here, the sample size, you will have more whats and then it's likely more than 10. So if you increase the sample size, so good on deeper understanding right there, if you increase the sample size, it'll become more normal via the central limit theorem, but also you're getting more whats and whatses. These 2 numbers right here, which represent those things up there. Because increasing n will increase those to be larger than 10. More successes and failures. Does that make sense? Success, failures. So by increasing sample size, there are more expected successes, expected failures. And if you have at least 10, then you're good. And don't worry if it's exactly, we've never put exactly on the test because numbers don't even exist. I could get into number theory, but there's infinitely many numbers between them. So they passed the conditions right here because we would times this by 0.37, and 37% of that's a lot. Like 37% of 100 is 37. And then the failures is even more. They randomly took it as far as I can tell, and it's less than 10% of all smartphones. So really, 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 wow. Oh, someone correct me. Somehow I misclicked. Would someone correct me? I said we pass all the conditions. So what words over there is right? I said we pass all the conditions. Unimodal symmetric, which is normal. There we go. What would the mean of this be? Well, now this is where we get to the mathematics of it. And if we pass the conditions, it sounds complicated, but it's the following. The mean or expected value of the sample proportion, that's how that reads, it's not math, it's just a sentence, is equal to P. And in this problem, P was 0.37. So what's the mean? As in, this is P, and we're trying to find this value, which is one thing. It's not a multiply, it's just one thing. It's 0.37. So we just take 0.37 and just drop it right here. That's it. Standard deviation? Yo. So now the standard deviation is, quote, 191 P times Q over N square root. P times Q over N square root. Someone go ahead and put Q in the chat for me. Someone go ahead and well, find what it is mathematically. So the standard deviation of P hat, which is the variation in it, is P times Q over N square root. What is Q? Bada bing, bada boom. Yeah, don't multiply those things. It's just a sentence. It's like standard deviation. What is the spread of this? What is the mean of this? Boom, Sarah's got it right there. And we're just doing 1 minus. So make sure these two values add up to what? If you've done this properly, those two values right there should add up to what? If you've done this properly, those two values right there should add up to what as I find this out? If you've done this properly, they should add up to 1 because they're complements. And that's a good review for the chapter on probabilities. So all we're doing is plugging in the numbers. The sample size was what? 437. We have to know the sample size. 468. 468. Be very careful, because when I say P times Q over N square root, it's not square root of N, it's square root P times Q over N square root, the whole thing. So just be careful on that. I've had people make mistakes. So look at your formula sheet, which has this on there. And this is the variation of it, like how much it spreads out. Variation, standard deviation. And there's the value. We're just going to bring it over. We're going to copy paste. Where'd our thing go? Pause. Oh, we didn't pause. Oh my gosh, what do we? I got to throw 2 seconds right here. That's, why did I not say pause? Because people are going to forget when they're doing the conditions. Here, when we do the next set of conditions, we'll pause. My gosh, how did we not pause? That's worth some 5,000 points. Remind me to pause, because a lot of people just go through the conditions so fast, and then they're like, wait a minute, I thought it was success failure. And I'm like, well, that's for proportions. They're like, well, how do I know when to do which one? I'm like, is it quantitative or categorical? So we usually try to start the questions by asking, are we doing a quantitative or categorical question? And now we've got some really good notes here for each of these questions. Why's in the chat? Homework 2. Here we go with this one right here. Now, this one actually shows the central limit theorem. And let's take a look at it. So take a look. The distribution starts to become more what as the sample sizes increase? As you go from a sample size of 20 to sample size of 50 to sample size of 75 to 100, two things occur. And what are the two things? The third condition would be large enough n if it's quantitative, Reagan. Reagan, thank you for asking. We'll make sure, we might try to do some of those today. It becomes more normal, and what other? Look at the number line, goes from 0.5 to 1, and at the end here it goes from 0.75 to 0.95. So as we increase the sample size, it becomes more normal, and also what are? Two things the central limit theorem says. The sampling distribution of the sample mean or sample proportion, it applies to both, becomes more normal, and what are? Because think about the number line here. Think about the number line there. The number line is getting smaller, so it's getting water. Starts with a T. Starts with a T. Tighter. Does everyone see that n is on the bottom of this equation, which means you're whatting by n? Tighter, exactly. So when you do standard deviation of the distribution, you're whatting by n, which will make this quantity smaller. Because think if n gets bigger, well, does that make sense? Just think mathematically. Because if n is a bigger number, you're whatting by a bigger number, which makes the quantity smaller. And that's the standard deviation, which is spread. I'm looking for a D word right now. I always ask for the word to make sure you're following along, and then you think it, you're like, oh, and that'll make it smaller. So literally, mathematically, we have right here the second condition. Does that make sense? Like you can see the second condition right here, where you're dividing by n, and then square rooting the quantity, but the dividing by n makes it smaller. Great job, William, right there. So if you understand the formula that as n gets bigger, the standard deviation gets smaller, you actually see one of the parts of the central limit theorem right here, that the number line here going from 0.75 to 0.95 is smaller because it has a larger n than the other ones. This problem can be tricky. It starts out left skewed, and then the good news is, if you get lucky on this, 0.85 is always going to be where the center's at because the mean doesn't change. Mu p hat is always p. So what you have to hope is you get one like I have right here, where 0.85 is in the center, and the sampling distribution starts out with a very wide range of 0.5, at least for mine. To find the range on it, does everyone see these numbers right here? The range is just big number minus small number. That's all it is. What is the range of the next one? What is the range of the next one? We're just looking at big number minus small number. We're on the next graphic. And it's going to show that it gets tighter here because it was 0.5 before, and now it's a smaller number. So what is the range of this one? So we're looking at the range of this graphic. What is the range of it? Max minus min. What is the range? 0.35. Great job, William, right there. Got to keep hitting the points buttons. So 0.35 right there. It's still, I believe, a little left skewed, and the center is still at 0.85. Now here's where we run into a problem because they have two values with 0.85 in it. So you have to look at your distribution, and you have to see where this peak is at right here. So then you start here and you go 0.65, 0.70, 0.75, 0.85 to 0.90. 0.85 to 0.90. You have to count across in the units. It's a bummer. Sometimes it's easy. So it's 0.85 to 0.90. And I usually give points back if you'll miss that. The range was 0.35, so that's relatively wide right there. Ooh, what's going on? Is it no longer skewed? Sample size of 50. Ooh, is it? Let me look at the math on this. No, it should be still skewed to the left. Relatively wide. We said is it the other one? Did I count incorrectly? Maybe I did. Let me check again. 0.65, 0.70, 0.75, 0.80, 0.85. Yeah. Let me show you again. So 0.65, 0.70, 0.75, 0.80. Yeah, it's the center because this is 0.80 to 0.85. So I did miscount that. I would give you points back on that. It's a little bit ridiculous. It's always going to be 0.85. So if you see, now we have another one we have to pick between, and this one has smaller units. So we have to go here and say this is 0.65, 0.70, 0.75, 0.80, 0.85 to 0.875. So it's the 0.85 to 0.875. Now we can check to see if this is normal. It's a sample of 75. What am I currently checking right now? Look at the mathematics and say, you can type two letters, like think of two letters, because I'm doing 0.85 times 75, and that's larger than 10, and 0.15, which is Q, times 75, which is greater than 10. What did I just check? Which means I'm going to go here and do approximately normal. So I just checked two numbers were greater than 10, so we're checking conditions here. Check two numbers are greater than 10. What condition did I just check? What condition did I just check? I think it's still relatively wide. That's the success failure condition. Success failure condition is NP greater than or equal to 10, NQ greater than or equal to 10. Now we could check to see, and it does say, it doesn't give the population size. They just did a simulation right here. But we'd have to assume the population is greater than 1,000 in this instance because we're doing a sample size of 100. And if it's already normal, it's going to be normal here. So, and the range is going to be smaller. Let's see here. 0.85 is in this interval. Do you see how that's the answer? Because 0.85 right there is in the interval, so that has to be the answer. It's going to be normal because it's already normal. It just gets even more normal. And then the distribution is a little bit tighter, 0.75 to 0.90. The range of this one is 0.20. So let's go and find one of the ones with the range of 0.20. And that would be relatively narrow right there. We never get the super narrow answer, but that would happen if we had an even larger sample size. So really good question right there. And great job. Thank you, Cameron. Good job in the chat. 0.95. Oh, what did I say? Did I say something incorrect? What did I say? What did I say? I don't know what I said. This one's a bit interesting. It brings up a new topic, 0.90. I think we're good, right? Someone might elaborate. Pew Research gave a poll to 1,058 adults. They responded about internet usage. 44.6% reported they are constantly online, as I am, I think too. Explaining the meaning of p hat. Well, what is p hat in notation? So go ahead and tell me what p hat is. What is p hat? I said 0.9. Oh no, I'm sorry about that. What is p hat as notation? Don't read their answers. Have in your notes, or know immediately, p hat is the what? P hat is the what? It was 0.95. It's kind of predicted. It's like this. You talk to 10 of your friends and 3 of them own a dog. Explain to me p hat and how it's found. So x would be 3, 10 would be n. So you talk to 10 of your friends and 3 of them own dogs. Find p hat and explain what it is. Exactly. And then what does that mean? What does that mean? What does it mean? So what does it mean? You're correct. Everyone's correct. What does that then mean? It's found via x over n. So we could find the amount of successes here. You could figure out how many successes there were by taking 0.446 times this right here and find out the amount of successes in the sample. Just round it up. 3 out of 10 friends had a dog, or 30% of friends had a dog. Great job, camera right there. Does that make sense? The proportion of your friends who owned a dog in your sample is 0.30. The proportion of the sample. So we need to look for sample proportion right here. Is that sampled reported? Here, this looks about right. This is the only one that says sample. So because, wait. No, that says confidence, no. It just means 44.6% of the samples said they're online. Now this is the standard error. Okay, so this is a small thing that we don't cover, but it's the same sort of idea. The standard error is about the same formula. The standard error won't be on the test. Question's good otherwise. The standard error, because I think it even shows you, get it wrong, is going to be p hat times q hat over n square root. How similar does that formula look? The standard error is p hat times q hat over n square root. So I think we had 0.446, and then we times that by 0.554, and then the sample size of like 10 something. Yep, it's virtually identical. It's when you don't know the truth, you use the sample as the estimate. 446, correct, 1058. And we just solve right here, p hat times q hat over n square root. We will use that in later chapters where we don't know p, because we don't always know the truth. And q hat is 1 minus p hat. It's the same thing as p and q. Oops. Tell me if I type something wrong or say something wrong. There we go, p times q over n square root. Put little hats on them. And there we go, round to 5 decimals. 1, 2, 3, 4, 5. I think it's got it. Should be right. We did it. Explain what this means. The standard error is an estimate of the standard standard deviation, but we can't handle it exactly. I got through 5,000 points. People were correcting me. I really appreciate that. I'm like, what did that say? Like, you said this. Everyone caught it. Everyone caught it but me. So I got through 5,000 points for the corrections. Please keep the corrections coming when I make errors. Please keep the corrections coming. I am not beyond making errors. The standard error is the best estimate of the standard deviation. That looks correct. Which measures, that's good. The standard deviation measures the variation. Oh, really? Let me see here. The standard error is the best estimate of the standard deviation of the sample distribution sample proportion, which measures the amount of variation in the sample proportion came from. Oh, because they're saying with the sample size, it's not margin error. Okay. Really what it is they just went way more specific on the last part. I'm looking at the difference between those answers. The standard error is the estimate of the standard deviation, but also it's for a certain sample size. So they went way more detail on that. They went to like the highest level of detail on that answer. So sure, it does have a specific sample size. As sample size increases, what 2 things will happen to the sampling distribution of the sample proportion? As sample size increases, what 2 things will happen? Don't worry about their answers. Know your answers. As sample size increases, what 2 things will happen, which the central limit theorem states? Think this and think this. You can just be like 2 things. 1, 2. So what are the 2 things that happens? As sample size increases, what 2 things happen? It gets more water and more water. Tighter and normal. Did you say anything about the mean? Did you say anything about the mean right there? Because we put questions just like this on a certain assignment. Did you say anything about the mean? Did you say anything about the mean right there? No. Because in this formula right here, does it have n in it at all? Does this formula have n? Just type yes or no. Does that formula right there have n in it? Does this formula where the mean of the sample proportion is equal to the true proportion, does that have n in it? Nope. So what happens to the mean if I change n? If n gets larger or smaller, what happens to the mean? Just to repeat, this is like memorization and then seeing it in the formula to be like, oh, there's the formula. It doesn't have n. So if n changes, nothing happens. So the answer is it stays exactly the same. Oh my gosh, what am I doing? I didn't get it wrong. So there's the mathematics behind it. As sample size increases, the standard deviation will do what? We'll do 4/5 because we're doing these so quick. As the sample size increases, the standard deviation will do what? Ignore the hats on these. As sample size increases, standard deviation will do what? It gets smaller because we're whatting by n. So just look at the formula mathematically and remember, oh, because we're whatting by n, we're taking the quantity and we're whatting by n. Dividing by exactly. So seeing it more and being like, okay, if n gets bigger, we get a larger sample, it's going to make the standard deviation smaller, which makes it tighter. Remember, standard deviation is spread. So good job reviewing these concepts right here. Excellent work. This is going to get smaller right there and also gets more normal. Okay, we got another question coming up right here. And great job. I really mean it. Like, people who are doing the work are doing really well in the class. So keep showing up here. If you're watching this later and doing the work, you rock also. Everyone rocks, but I want people to get great grades. That's what I want. So suppose 30% of your town talks on their phone while they drive. Haha, that's bad. Don't do that. What 2 quantities do we know? Good to see you, Jennifer. 30% of your town talks on their phone. And we haven't mentioned samples at all. What 2 quantities do you know right now? 30% of your town talks on their phone while they drive. 2 things you now know. You want to write these down and be like, okay, I now know this, and I now know this. When you do problems, think about the numbers and always note what the numbers are. So 30%, yep, P and Q, exactly. P is 30%, Q is 70%, and they're not from samples, they're supposed truths. We're going to suppose these are the truths. Great job, Sarah and everyone. If you're still on a busy street corner and you watch 50 people drive by, now we know N, right? 50 is N. About what proportion would you expect to see drive by? This is the question. We are merely trying to solve this formula highlighted in green. So what is it going to be? We know P. So it says, what proportion would you expect? And this reads expected sample proportion. That reads expected sample proportion. That was easy. Now be careful, this question changes up because it could say how many. Think about this. If the question said how many, which is another version of it, losing my cursor. Where did it go? There it is. If the question said how many, it'd be what? If it said how many, because that's the sample size, that's the expected sample proportion, and that's NP right there. That would be how many. No. Yep. And another one. Exactly. Great job, Sarah. And that's checking NP technically, like the expected amount of successes right there. Good work. Next question. If you notice, we've done the conditions. We've done so much. Chapter 15. I usually go slower at the start, and then we build up our knowledge, so we've got all the knowledge needed. So when you get a question on the test, you should always mark your notation. So what should you do when you get a question on the test? And I'll do it here as you tell me and remind yourself. When you get a question on the test, what should you do? I'm doing it right here, right now. Remind me in the chat for some points, for a little bit of points. So what should you do? Mark your notation. So that is the true proportion. Here's the complement. We just do 1 minus. So just do 1 minus that. You should get that right there. This is based on a random sample. And this is n. Is it really? Well, think about this. And if we assume those are truths right there, if we assume the truth is close to those, write what you know, mark your notation. So do you think Pew takes a random sample? Do you think a random sample? And how would you know that in this question? Do you think it's a random sample? Condition 1 is random. Did we take a random sample? So do we know that? What do you think? It says random, you bet. That's condition 1 right there. The next condition is condition number 2. And I'll highlight what's important for condition number 2, which is we're talking about American adults. So we have to ask the question, are 1,400 American adults less than 10% of all American adults? So do you think we've taken less than 10% of American adults? Do you think we've taken less than 10% of American adults? Because we've taken 1,400 of the total. We've taken 1,400. Yeah, there's got to be at least 14,000 American adults then, so we're fine. Think about, okay, there has to be at least this many. If you times that by 10. Yeah, exactly. Great job, Sarah. And that's the deep understanding I want people to have on questions. Throw Sarah some points right there. Now, how do we check the success failure condition? So just type in the chat for me the 2 quantities you need to see are greater than 10. And we've got the things listed right here so we can find them pretty quickly. So you need to see what 2 things are greater than or equal to 10. I'll start doing the math. Here's one of the quantities. I'm going to times it by n. There we go. There's one of them, NP. And then if you look at it, it's going to be fine because it's a very large sample size. So we're doing this right here. And by passing all the conditions, we have NP and NQ greater than or equal to 10. We have a random sample. We have less than 10% of the population sampled. And by passing all the conditions, the distribution should look what? By passing all the conditions, and that's not it, but how it looks. By passing all the conditions, the distribution will look normal distribution. So we have passed the conditions. We're good to go. Now it's on to seeing what the question says. So yes, we pass all of them. Has at least 10 successes. No, less than. No, at least. See, look how little you would learn if you didn't cover the. If you're like, oh, that's the right answer. Just do that right there. We have a random sample. We took less than 10% of the population. We have at least 10 successes, at least 10 failures. Know how to check each of them. Check the start of this when we went through it a lot slower. And you should be able to get it right there. We are going to finish this homework. I can tell. Chapter 13, homework 8. Okay, for his final project, Stacy plans on serving a random sample of 90 adults. Immediately write blank equals what right now? Immediately write blank equals what? Blank equals what? She's going to sample 90 adults. N equals 90. Great job, Sarah, right there. N equals 90. And then from past years, she guesses that about 8% of her class goes. So what should you write there? 8% of her class goes. Yay! Great job right there. Great job on the Canvas content. And that's more like the test. So nice work, Cameron. So she guesses about 8% of her class goes. So what should you write there? If she's guessing the truth is 8% goes. P equals 0.08. So let's say Stacy goes to a really big Florida school. No, you're fine, Cameron. If she goes to a big Florida school, which condition do you think I'm talking about? 90 students is probably what? She's sampling random samples, so random is passed. But 90 students is probably what? Well, keep going. I see 10%. Keep going. I would say 90 students is probably what? Less than 10% of her school. Does that make sense? So we're probably good on the less than 10% condition. But here's the problem. What condition do we fail and why? Can you solve this one? Use the conditions of random, which we pass. 10%, 90 students is less than 10% of her school, so we're probably good there. But what condition do we fail, and then why? So, but show me the math. Show me the math on what condition we fail and why. Show me the math. Boom, 7.2. You got it, Sarah. Exactly. Sarah, great job. Did NP right there. Because we already know N, we know P, and then we check NP, and it's less than 10, so we fail. Is it making more sense, Sarah? Just checking these conditions multiple times. That's why we mark the notation. If you have N marked, which is 90, if you have P marked, which is 0.08, you multiply and you get NP as 7.2, which is less than 10, meaning we failed the success failure condition. The other one would be 82.8, around there. And so no, because the success failure condition is not met. So make sure to do the math right there, and we're good. That's all it is. Only a few more to go right here. I hope the conditions are making a lot more sense, because we've been reviewing them a lot today. Here we go. So a philanthropic organization is doing a fundraiser where they have 5% success. Now what you see right here is a simulation. What should the mean be? If 5% of people respond to a mailing list, then what should the mean be? And then you took a sample, what percent would you expect to respond to the mailing list? Like if 5% of people generally respond, you'd expect what? You go out and talk to 100 people, you'd expect what percent to respond? Think percent though, because I know it's 5%. That's why that is the theoretical mean. Does that make sense? The theoretical mean is 5%, but then when you go out and do it, you might see something a little bit different. So 5% is the theoretical mean, as in we expect to see this. Now, the fact that you see something different is probably just random variation around it. There's also the theoretical standard deviation. We could find these. Watch this right here. Is if we go right here and go P times Q, 1 minus, over N, square root, and that is the quantity you see up there. P times Q over N square root. And you could do each one of these and get each quantity below, just finding the theoretical standard deviations. And the theoretical values are close to the truth. Now, if we have 5% successes, how many successes would we have at a sample size of 100? If we have 5% successes, how many successes would we have at 100? Your question could be different, so make sure to check what I'm checking right now, because they do mix it up. You need to know how to check this, because if we have 100 sample size and we have 5% successes, we'd have 5 successes, 100 times 5%. So what am I pointing out to you right here? And when I look at this histogram right here with 100, I'm like, eh. Like I look at that and I say, Because 5 is not what? Success failure condition. We just did NP, so we just checked the success failure condition. 5 is not what or than what. I'm going to be like, it's not good enough. We failed the success failure condition. We didn't get at least 10 successes and at least 10 failures. But at 200, which, at 200, we have how many successes on the dot? At 200 with 5% successes, we have how many successes exactly? So with 200, we have exactly 10 successes, so 5% of 200. So with this in mind, we're going to say 200 is what we need to get. Got it. Check your success failure condition. They do mix that one up. What does success failure condition say? At this point, we have at least 10 successes and at least 10 things. So is less than 10 at least 10? No, wait a minute. Both are at least 10. We need at least both of them, so they're checking both. That's a very good question, which you can just click through. So don't click through it. Don't be like, oh, I saw. I'm so afraid I want people to know how to check it, because on the test, we literally have you check it. We're like, is it met? And then if you know, and you just do the math. And you say, oh, I know how to check the success failure condition. That's easy. A machine of soup cans, putting them out with some variation. We have 255 batches right here. Would a normal model be useful to explain the sampling distribution? No, the sampling distribution is less skewed, so normal would be not useful. Is this the sampling distribution? Yeah. Okay. So we shouldn't use it. Why? So it's A. Yeah, it's just not normal. I don't love that question. So you shouldn't do it. Just don't do it. Don't use the normal. 68, 95, 99.7 is based on the normal. Our whole 68, 95, 99 point. I was double checking. I was afraid I got one wrong at the start because I just like misread the unimodal symmetric. And I'm like, are they trying to trick us right here? They're trying to trick us. But we should have 100 on that homework, another homework done. Do we have enough time to do like one quiz question maybe? What do you think? Is there a quiz question that has people stuck? There's ones like on voting and stuff like that. There's some tricky ones on this quiz. So you're welcome, Hannah, right there. Really proud of everyone. People should have hundreds on the homework now. Like, even if people just like put in the answers I put in, that's better than not doing it. I'm always afraid. I always want to teach it, but no. If you put in the answers, that's still a good thing. I mean, it's, you know, you still get points. Got ahead to class. You're welcome, Sarah, and great job right there. Thank you, Sarah. Good work. Get that 100. And you can always come back later to check out what we do. Let me see if I can find a quiz question. A quiz question. Oh, fall asleep. Quiz question. Not that many quiz questions. I probably did some of them. Did that one. There's a really tough one here. People usually ask about this one. I'll do this one here to end, since people usually ask about it. It's not that bad, though. We'll have time for two more. Okay. The proportion of adult women in the US is approximately 51%. What three things, and then we have 400 random surveys, what three things should you write down? Try to right now write down the three things for this question you would need to solve it. So as I take a screenshot right here, can you write down the three things that are going to make this question super easy to solve? And we notice we're talking about, is someone a woman? And that's going to be proportions. So what are the three things as I write some equations for you? So if you know you're talking about, is someone a woman? And that's going to be the mean of the sampling distribution of the sample proportion is equal to P. And the standard deviation of the sampling proportion is equal to P times Q over N square root. Boom, William's got it all right there written out. And William, you notice from here, you can just plug in the values. So William's already got everything written down right there. And William found that this is P, which is the true proportion, and then Q, which is the complement of the true proportion, and then sample size, which is how many we spoke to. And so what is the proportion of the sample you'd expect to be women? So we literally just plug P in right here, and the answer is literally the same thing. So because if you talk to a certain amount of women, you'd expect 51%, because that's the truth. Good to see you here, Emily. And then we plug in P times Q over N square root. A lot of this just boils down to knowing your notation, because if you know the notation, not that bad. And so what do you think? Are people less worried about this chapter now? If you know the notation, these chapters are way easier. Way easier. I agree, right, William? It just comes down to a lot of practice. There's that. And then how many women would you expect? So actually, this is actually the success failure condition, checking one of the two. So since it says how many women would we expect, what is the mathematics right here? Blank times blank. So how many would you expect? We'll be doing chapter 13, part 2 in class today. What is the mathematics right here that goes into these blanks? What is the mathematics that goes into those blanks? What is the mathematics that goes into those blanks? It's the math. How would you figure out how many women you would expect in this sample size? You're welcome, Emily. You got it, William, right there. We just take 400 and we do N times P. That's it right there. That's all it is. And that's going to give us 200.4. I think I'm off a little bit. Nope, 204. Wow. Yeah. I just moved the decimal wrong on the last part of that. That's got it. It's not a bad question. It's a very good one, actually. This was 0.025. And this was 51%. Should do it. Check answer. Yay! Try to do one more right here. This one's not the best. Don't love it. But what percent would you expect to see on their cell phone? I already did that one. What is the standard deviation? Well, the only one that looks to be like a standard deviation is that one. So all those points. As sample size increases, the mean stays the same. The standard deviation gets smaller. Another view histogram 1. Another view histogram 1. Does not pass the success failure condition. We did this one just earlier. So right here, I'm just burning through these. So 15% of this, you need to look at 15% of it, success failure on it. So 15% of 75 is enough. So 75 would be large enough. And there's at least, there we go, that should be it for that one. Any questions? I'm actually just seeing how many I can do. I can almost get through the full thing. 48% of the sample. We're speed running it. Is that the sample size? 20,000? No way. Oh, it is. Just 7 decimals. 1, 2, 3, 4, 5, 6, 7. Gonna round right here. What? The standard error is the best estimate of the standard deviation. There we go. That should be right. Did I get this wrong because of the decimals? Got to put a number here. No, I got that one right. What did I make a mistake on? Standard is the best estimate of standard deviation. That's right. Okay, so I got this one wrong. The meaning of p hat is that 48% of the sample. No, it's the best estimate of p. There we go. It's because, so just little thing, didn't catch that right there. Does everyone see that? P hat is the sample. P hat estimates p because p is the truth. So I just read the first part of it right here and didn't notice later on it says that this is the researcher's best estimate of the true proportion because the sample estimates the true proportion. Damn. Like, can I do the whole thing? Same question right here. We have to find p hat, q hat. So p hat is 0.45, q hat is 0.55. Divide by the 1058 square root to get standard error to 5 decimals. 1, 2, 3, 4, 5. Round up. And it's the sample reported best estimate of p right there. Stats SI group is asking, do you know how when data analysis 5 and 6 will be graded by chance? The graders are supposed to do it in 1 week. They have 1 week to do it. And I probably got to talk to them and be like, hi, it's been 1 week on 5. So they have 1 week to do it. And I can probably go and unhide my grades. Let me go and do that right now to finish off office hours. Because I think there are some hidden grades. But they are supposed to do it in 1 week. 1 week. 1 week to do it. That is their grading timeline. And we try to talk to them and say, hi. Be right back. Got a 2-factor authenticate. 2-factor authenticate. There we go, 2-factor right there. Just gonna walk in front of the green screen. All right, let me see if my grades. Grades are over here. We'll end off with this. Head over back to here. Okay, let me do 1 week. I think most of 5 has been graded for my class, or at least half I saw. And it was turned in a Friday ago. Come on. It takes a while for Canvas to load. Come on, Canvas. Data Analytics 5, it's still hidden. Let's post grades. Okay, grades are being posted. I've got them in trouble. Got who in trouble? No, I mean, I'll message them and I'll say, hey, just want to check in. Data Analytics 5 should be graded. Let me do that right here too. I'm gonna message them too. No! Let me see. Messaging them as we speak. Gonna be like, hey, just checking in. So, check in. Dating. Should be. Thanks. All right, cool. I'm messaging. There we go. Message them. I'd rather just jump than write about it again. I know, right? So, there we go. They should be posted now. Or the ones that have been graded are posted now. Been pretty good. No. Mail. Yeah. Over these. It's got it. So what are the odds we raise the max from 1.03, the points? I can't believe I have a 97 in here still. Oh my god, math is my weakest link. I shouldn't have said that now. Well, no, Karen, I'm not an 88, I've been really good. That's awesome. So the teaching style helps you, I hope, Emily? Is like, are you doing good in spite of the teaching style, or like the teaching style helps you? Like, I'm trying to like understand, like, it's like, I've been doing good in spite of the teaching style, or you make it not scary good. We have a little bit of fun here, you know? It's good times. And I can hear the music now. Yes, and you can hear the music too, I think, now. Yeah, nice chill music. Awesome, well, thank you so much. Grades are posted, we'll check them out. Until then, bye for now, everyone. Bye. Heading up. Beautiful music. You should hear the music. Wait. No, you don't hear the music here. Wait. I'm fixing it so you hear the music on all screens. Okay. Here we go. I'm doing work right now. Okay, you should hear the music here. You should hear the music here. You can hear the music there. Where else would you need to hear the music? Oh my god, illusion broken. I should hear the music on all screens now that matter. I think that's got it. Boss file screen, need that too. There's the music. I'm copying things between layers. Oh my gosh, Ethan, good to see you there. Till then, bye for now, everybody. I'm gonna go play some guitar. Woo! Still got the music going.